Okay, hello everyone, and thank you to the organizers for this opportunity to present the results of this project that I think that has nice results. So I'm a postdoc in the Instituto de Astronomía in Ensenada, in Mexico. So here this is like a brief introduction about how we consider that the evolved stars are those producers. So here it's just a HR diagram where we have some examples of this. This is in the scenario where we have a single star evolution. So here we in this kind of star we present sometimes a ejection material or cloth or wings that eject enough material that will reach the appropriate temperatures and high densities to in order to keep the dose formation. So here there is an example of the work that is in the group where we try to model the infrared observations, the infrared set, based on infrared instruments as WISE, Spitzer, and Herschel. So here we have some examples, and we try to model this emission. Using a specific example where we have the nebula RCW58 around a world rate 40. This we try to model two specific regions in order to see in order to characterize the dust properties. So here we use as input parameters those type of species like silicate and those grains with two populations of grains, with the smallest grains and big grains. Also, this is important. In order to reproduce these observations, we involve a high gas to those regions. So this is important. We see more in the next slide, why. So this is our motivation for this project. Also, we can obtain from this model the amount of gas in this nebula and also the amount of dust in this nebula. And this dust is important because if we're considering that it's coming from the central star, so this dust has the information of the last stages of the star and could tell us a lot of information. So for this model, for these models, we use the photoionization called cloudy. Why? This is because we can model simultaneously the gas emission and the dust emission. So here is a cartoon where we have how works cloudy. Here we have a central star and surrounded by a nebular material. So we need as input parameters the incident radiation field over the nebula, works very much. But also we need the luminosity of the star, and also we need the information of the nebular material as the gas distribution, and the information of the dust grains as the grain size, chemical composition, and the amount relative to the gas. In these objects, we use as observational constraints for the emission, for the ionized gas emission, the optical emission lines as H alpha and H beta. And also, if we have available the radio continuum observation, that is, in order, if we are assuming that we have a free emission at these frequencies. Also, in the case of the infrared emission, that is from the dust emission, we are using the shape and the flux of the infrared photometry. So these constraints is in order to apportion models to a realistic object, right? So with this in mind, we use a stellar atmosphere model of the central star for specific for each object that we model. So here is an example of where we have a stellar model of a working star in comparison with a black body. So if we're considering the most realistic parameters in order to model these objects, also why we are forgetting uh, some assumptions as the dose opacity. So Cloud is using the dose opacity considering different assumptions as the geometry, composition, and the size parameter. This size parameter is telling us how is the interaction, how we can estimate the interaction of the particle with the light that uh, is inside is is coming to the particle. So this is important parameter. So in CLADI, we are assuming from the database that this will have spherical grades. This is based on the mean theory. However, also there are some works that are trying to invoke ellipsoidal grains, but it's based on the kind of modified mean theory in order to give this dose opacity. And then if we want to introduce these realistic particles, we want to use irregular particles. Here, for this reason, we decide to use introduce these particles using the Tamodos 2020 database. This database has the single scatter properties of variety of almost of the 20 particles that is given for different ratio in size, where we have the ratio is the wide of the particle with the longest axis in the particle. So Tamodos also is working with two kind of kernels, where we have here that is considered the short Webel kernel and the long Webel kernel, and this is the constraints of for each kernel. And in order to use or obtain the data in this database is using methodologies as T-matrix for the smallest values of the size parameter, and for the larger values of the size parameter is using geometrical optics. So basically, Tamodos needs as input parameters the maximum dimension of the particle and the specific wavelength and the refractive index of this particle, of this grain, this species of grain. And also we need to set the sphericity. And we will have as output the wavelength, the diameter, the maximum diameter, the projected area, the volume, and also the extinction efficiency, the albedo, the symmetry parameter, and the phase matrix. This is not needed here for our work. And now we decide to work as a first approach about MR size distribution. So that means that we have as the minimal size grains as 0.05 microns and the maximum grain size as 0.25 microns. And we decided to work with 10 beams in this distribution of size. And also we have like a small distribution of size here in each beam. And so we obtain the single scattering parameters for each size between these two between these two size of grains, and we integrate in order to obtain the bulk of the properties of the grains. And we set as a first approach a sphericity equal to 0.7. And also we use as a data from silicates, graphite, and amorphous carbon grades. We obtain the refractive index for these dose species in this project. So this is the first result for silicates, where we have here plotted the efficiency extinction versus the size parameter, the single scattering albedo versus the the size parameter, and the asymmetry factor, and the imaginary part of the refractive index. Here, I'm not sure if you can see, but the solid lines is indicating that is the data that we can move into the, or we can use with the database models. Okay, so we have this, and also from this is the same data, and so we use these equations in order to obtain the cross section. That is the cross section that we need to run models in Cloudy. However, we have here a problem because if you can see from the laboratory data, we have a short range of wavelength. So that means that we have a small range that we can work, and Cloudy needs to run models needs a wide wavelength range because has from the X-rays to almost the radio frequency. So we have a big decision here. So we decided to divide our data into the set 1, set 2, and set 3, where we have the small and intermediate and large particle regimes. And we need to, and for the intermediate, we use the Tamodos data, and for the small grains, for the small, we need to use the spherical or the ball approximation. And for the case of the large particle, we use the also spherical approximation here. And we obtain these cross sections here, that is in the solid lines is our the data coming from the tabotas, and the dotted lines are coming from the spherical grains. This is for this case. And so now we can draw Cloudy models. Here, this is a input data for our models. We are running two shells, one shell with just gas and the other shell with just with gas and dust. And we are trying to mimic a model that I have presented previously of the RCW58. And here is in this plots we have the continuum of the models. Here is just I'm presenting for the smallest grains in the size distribution, and for the largest grains in this size distribution. And here we have in the last one we have the complete size distributions. And in order to prove or see what is the difference in fluxes, we have to perform the ratio of the fluxes, the synthetic fluxes obtained for different telescopes. So we can see that for the smallest grains, we have difference, but it's more noticeable for the larger wavelengths, and for the as well as in the largest grains. So this is the case for graphites, amorphous carbon grains, and it's the same case that silicate grains, where we are constrained by the optical data from those species. And here is the result of the cross sections, where we have difference between the spherical and the hexaedral grains. And this is the results for the models for each species, and you can see how we present difference for each those species. Also, something is different. Something is important here that the diamonds indicate the peak of the infrared peak. This is important because when you want to set the largest grain size that is the grain size that is dominate the mass of the nebula, this indicates for this peak. So this could tell us too much information. And here's the result in the case for the graphites, where we have a big difference in the case for the largest grains, and even if we are using just 0.25 microns. This is the case for amorphous carbon. Also, we have difference here, but also in the small wavelengths. And also we present here for the case of PE amorphous carbon. So this is my conclusion, very fast, because These models is not also different in the fluxes in the continuum. Also, is also different for the temperatures of each species of the grains. If you can see also here, the solid line is for the irregular grains on in the dotted lines is for spherical grains. So we have different. I'm sorry. Thank you.
I think we have time for a quick question or two.
Oh. Camila, nice job. Can we expect to have different values for the temperature or the mass that we estimate from the observed spectra by using more realistic models for the dust?
Yes, because
How much?
how much? How much? I'm not sure about the mass, but for example, in differences. Here in the example, here in the largest grains of the graphites, you have a difference almost of 60% of the flux. So that means that it's a big difference with we don't need to invoke a high values of the dust to gas ratio. That means that we need less mass of dust in order to reproduce the observations. That's what this one.
Maybe one more question, if anyone has. The back.
So if you are planning to expand to also other dust species, so which dust species can you study through this process, apart from this that you showed?
Yes, I'm planning to extend. This is the field results, but I'm planning to extend to other species. I'm planning to extend to other sizes of grains. I'm planning also to. The next step of this work is using in a real object, so we can see the difference. More with more quantities, but yeah.
Okay, let's thank Palmira again. Next up, we have Jaime Alonso Hernandez on characterization of the dusty envelopes surrounding HV stars with ultraviolet and X-ray emission.
Hello, everybody. My name is Jaime Alonso Hernández. I'm a PhD student in the Spanish Center for Astrobiology in Madrid under the supervision of Doctors Carmen Sánchez Contreras and Jorge Sanforcada. I would like to take this opportunity to thank the organizing committee for giving me this opportunity to expose my work in front of such an excellent public. And today I'm going to talk about our ongoing project in the characterization of the dusty envelopes surrounding AGB stars with ultraviolet and X-ray emission. Yeah, in first place, a quick summary of which are these UV emitting AGB stars. We all know that it is very challenging to identify binary companions, stellar companions in AGB stars due to their huge luminosities and intrinsic luminosities. So, however, one of the things is that the flux is concentrated on optical and larger wavelengths. So, if we identified AGB stars with ultraviolet excesses, we can propose them as binary candidates. This was done by Sahai and collaborators, and they identified a sample of AGB stars with these large ultraviolet excesses. This ultraviolet emission is also interesting in the sense that they have different time scales of variability. Here is an example of low time scale variability, hundreds of seconds. And it has been also identified some sources with X-ray emission. This X-ray emission seems to be more related with accretion processes. Okay, regarding my work, I'm going to divide it in three sections. The first one is about the characterization of the molecular gas in the envelopes. The second one is an exploration of the effects of this emission in the molecular gas chemistry. And the last one is about the characterization of the dust components of the envelopes. One important thing to remark is that in IRAS color diagram, these UV AGV stars are located in the left lower corner. This means that the envelopes surrounding these AGV stars are small, and if we take a look over the statistics, near ultraviolet emission seems to be in some way more common, but far ultraviolet emission is less common. We performed a survey over CO emission lines in a sample of 29 UV emitting AGV stars with the IRAN 30 meters telescope here in Granada. Here is an example of the CO emission lines. You can see that there is the typical variety of line profiles, which is common in these expanding envelopes. We perform a basic analysis based on the rotational diagram method, and we estimate the column densities and excitation temperatures, which allows us to derive other parameters of the envelopes. We found that these envelopes are consistent with radiatively driven winds and with those of larger sample of AGV stars. In addition, we also identified that the intensity of the CO lines in comparison with the far ultraviolet, far infrared emission is statistically lower than in larger sample of AGV stars. This could be an indication of a higher degree of photodissociation. Yeah. Regarding the second section, it is well known the effect of UV emission in the circumstellar chemistry. From the pioneer works of Agúndez and collaborators to the more recent work of Marie Van de Sant. Here is an example, and you can see that in a carbon-rich AGV star, the photodissociation of SiO liberates oxygen and produces an enhancement in the abundance of molecules like water. In this project, we propose two views of the X-ray emission, of the effect of the X-ray emission in the molecular chemistry. From one side, it is more observational based on a spectral survey in which we target H2+ as a well-known tracer of X-ray driven chemistry. And on the other side, we also propose chemical kinetic models to explore the effect in other view. Here are the sample. We have a sample composed of 4 sources. 2 of them are rich and the other 2 are carbon rich, and 2 of them have ultraviolet and X-ray emission, whereas the other 2 only have ultraviolet emission. We found H2+ in one of the sources, in the carbon-rich X-ray emitting tetraconis, and it also show a richer chemistry. Here on the right are the line profiles of the 2 detected H2+ lines, and you can see that there is some time variability between the 2 observational campaigns in 2020 and 2024. I would like to highlight 2 results from this study. The first one is related with the abundance of the CO. We found from both the chemical kinetics models and from the modeling of the line profiles that it is some kind of central depletion in the abundance of CO. This is related with the direct photodissociation of CO by X-ray photons. And the other result I would like to highlight is the abundance of H2+, which is enhanced by the presence of H3+. H3+ is produced by the photoionization of molecular hydrogen, and is a real game changer in terms of molecular chemistry. Okay. Now I'm gonna start with the last section of this talk regarding the characterization of the dust properties of these envelopes. For this purpose, we apply a modeling of the spectral energy distributions of the sample of the first paper. And here is an example. We gather some multi-wavelength photometry from optical to far infrared. I also perform photometry with archival Herschel PACS images, And we also gather some Gaia optical spectra and IRAS aniso infrared spectra. The strategy for the SED modeling is based on this, on the dust characterization, is based on this SED modeling, which we do with Comarch stellar models and dusty radioactive transfer code. In addition, I'm going to show you in 2 slides a check and comparison with the PAX radial intensities. Okay, here is an example of the modeling. We have to assume some of the dust parameters, but we propose 5 free parameters. The stellar temperature, the temperature in the inner radius of the dust cell, the density power law index, the opacity at 550 nanometers, and the ratio between the other and the inner radius. You can see that even though there are the parameters are well constrained in a one-dimensional view, there are important degeneracies between the different parameters of the dust. Okay, this was a check that we can perform because we noted that some of the targets are angularly extended, some of them are semi-extended. There is also one with a large scale detached envelope. And this allows us, because some of them are more extended than the Hasselblad PSF, so this also allows us to check that the radial density profiles are compatible with the models and check that everything is doing correctly. Okay, here are the histograms of the different parameters, and I would like to resolve some easy results. From one side, there are some AGV stars with doesn't have a dusty envelope, and these ones have higher stellar temperature. This is well known because as the AGVs have a mass loss, they also decrease the temperature. The temperatures in the inner radius are consistent with the sublimation temperatures of the gas. Some of them have even significantly lower temperatures, which is interesting. And the rest of the parameters are in comparison with larger sample of AGV stars. I would like to mention that we are exploring the gas to dust ratio because there are some recent papers that indicates that there could be some effect in this parameter. For example, the photodissociation of the molecular gas can reduce the gas to dust ratio. There is also an effect in the abundances of molecules which are precursors of dust. This can be also affected. The dust properties are usually not well constrained. As Taisa showed us on Tuesday, I guess, binary can enhance the dust productions, the production of dust, and there are also some binary induced structures that can affect the modeling of the CD and can lead to an underestimation or overestimation of the dust masses. Okay, so here are a summary of the main conclusions. We have characterized there is no evidence of affected dynamics in the CO emission lines. We have characterized we did the first characterization of the molecule of the impact of internal ultraviolet and X-ray emission in the molecular chemistry. There are important and multiple degeneracies between the SED parameters. We have found some very reduced gas to dust ratio, which can be related with a variety of factors. And finally, more observations are needed, especially interferometric and near and far infrared spectra. And just mention that I'm looking for a postdoctoral position to start in exam. Thanks.
So do we have,
Class.
Thank you. Can you say something about the companions? Because, for example, YGM has been confirmed to be a symbiotic star, so the companion is not welcome. What about the rest of the other objects?
Yeah. Well, my work is not focused on the characterization of the companions or on the ultraviolet or X-ray emission. It's more on the characterization of the circumstellar envelopes. But one thing that I did not mention is that one of the of these slides. One of the criteria to discern whether it could be related with binarity or with chromospheric activity, for example, or other issues, is the food to noof ratio, the in some way the ultraviolet color, and this is also very affected by dust attenuation. Is affected different in carbon and oxygen rich AGB stars, and can produce significant effect in the ultraviolet in the observed ultraviolet fluxes. So this is algo to take into account for the characterization of the companion too.
This talk, interesting results too, and perhaps you're aware that some protoplanetary disks have shown variable HCO plus emission. There have been some dedicated campaigns to try to see if variability of the host remain sequence star and X-rays might be responsible for the variability in the HCO plus. And I don't know that they're conclusive yet, but the variability is certainly seen. I think in HCO plus more than any other species that's seen in a protoplanetary disk.
Yeah.
I remember when we observed TW Hydra in 1997, and then someone else observed it like 5 years later and got a very different result for HCO plus. I thought I made a terrible mistake, but I think it's just one of many examples of variable HCO plus emission. That's
Yeah.
fascinating.
The idea we propose in the paper is to perform monitoring with both XMN Newton and submillimeter facilities to better constrain this variation and its relation with the variability of the X-ray emission. But it's future. Thanks.
So I have a question. I think we still have time. Could you go back to where you were fitting the abundance profiles? Well, there we go.
Here.
Yeah, so here you've got, I mean, there's a bit of a difference between the radiative transfer fit and your models, but is that sort of an important difference or is this within the uncertainties?
Is within the uncertainties. Good question. Yes, well, the blue line is the one which better fits the line profiles, and we did some kind of ad hoc profile. We have also more recent observations from NOIMA interferometer, and we now have seen that there is a big spiral, which is also affecting the line profiles. So in the future, we will have to take this into account too.
Yeah, and does the size match what you got in your models?
Yes, the size of the whole envelope is according to the models. Yeah, you can also see that the HCO plus is focused on the center of the envelope.
So let's thank our speaker again. And next up we have Guillermo Quintana Lasati.
Well, the title is right. So.
Talking about chemistry in the HVC, April 2233.
Hi everyone, and thank you for giving me the opportunity to present these results. I'm going to talk about the chemistry in the HVC FATL 2343. No, that's not that one. 2233. And you might wonder what's an HVC. And those objects are carbon-rich AGB stars in principle with high expansion velocities. And here comes the problem, because expansion velocity depends mainly, among other things, on the luminosity. So to have the width you see in these objects, which is like expansion velocities around 30 kilometers per second, instead of 15, which is what you would expect, you need to claim large luminosities that are supposed to be only for massive stars. Okay, but these massive stars undergo the third trap and also hot bottom burning, which transform themselves. This is not working, or this is the I will point to that. So these objects should be oxygen-rich stars, right? Which are not. So what do we know about these objects? Well, we know some things. They present a mixture of properties. They have a carbon-rich chemistry, as we will see now, but it's already observed in, for instance, with ISO. You see features that are clearly related with carbon features. They also present a high C2H abundances, typically 5 times what you will get in standard carbon-rich AGVs. But on the other side, they present large periods, which have been related with hot bottom burning, so massive stars, and HCN 120 with respect to CO120 is really large and was proposed to be related with a nitrogen enrichment, which again is related with massive stars. What we made in the past, I doesn't said myself, which it was in 2019, was model 2 of these objects, and we observed that the luminosities were high, pointing towards massive objects, and also we modeled CO maps, 1 to 0 to 1, and saw that the mass loss rates were high, again pointing towards massive nature of these objects. We proposed that it was that we might be in a case proposed by Amanda Caracas, saying that when you have a massive star, you have hot bottom burning, but this won't last forever because as these objects start ejecting material, the pressure on the core gets lower and lower, and at a certain moment, hot bottom burning stops. As you still have the third etch, these objects go back to the carbon-rich regime. So this will be very evolved, massive stars. Okay. Well, so I want to focus now on FHEL 2233, and we wanted to know about its chemistry, if it had some kind of hints about the massive nature and so on. First, we obtained maps with NOIMA of the certain selector lines. Those are azimuthally averaged radius of the emission. We also went for the 30-meter and obtained a full 1 3-millimeter and 1 millimeter line surveys, plus we count with hi-fi observations from the past. In total, like roughly 200 features coming from more than 30 different species. So first of all, we went back to Gaia. Gaia data release 2, the distance for this guy was not really robust, but for data release 3, it was. So we had to check everything we made in the past. And actually, it was a bit of change. We went for 4 kiloparsec to 1.2. So maybe not massive anymore, but we checked the SED, and we went for 10 to the 5.4 luminosities to 4.3, which still points toward a massive star, depending on the tracks you check, from 4.5 to 9 solar masses. Okay. We modeled again also the data we had of CO, and we had to fit 4 different shells. So, but now we had a density profile and a temperature profile to play with. We went to the lines where we did the rotational diagrams to get the density and temperatures. In some cases, we were able to fit 2 different components, but in others, we have to do just one. And these were the results from the maps. We knew where more or less several of the lines were emitting. We could estimate from the density profiles from CO the column density of hydrogen for the different regions. So we could transform the column densities into real abundances. I want just to focus in several of these results, which I find the more interesting. For instance, the abundance ratio of C2H versus C4H is extremely high. It's almost 60, which in general, what you find, for instance, Sci-86 or ISA 10-16 is roughly 1. So to try to explain this, those are the reactions you have to form C2H and 4H, which are extremely connected. You have also this path, but this path is less abundant, less important in general. So we start wondering why we have this very high ratio. So this is, well, they are connected. Once you have acetylene, you form C2H, and then from there you form C4H. And as I mentioned, Asunción Fuente and Pepe Cinicharo found a really high abundance of C2H, and they claim that it was due to the velocity of these objects, the expansion velocity, so due that the acetylene doesn't stick into the grains as fast as it should in low expansion velocity objects. And then when you reach the photoissociation radius for acetylene, you have more acetylene to form C2H. But the point is here is that it will also affect C4H, so you will still have a ratio of 1, right? So, well, this is again showing that this is from IST 10-16. With ALMA, both species arise from very same regions, so the formation is coupled. So we wonder, well, let's remove acetylene, so this path does not important anymore. So we just form this by IC3N, but we have a C3N, so this cannot be the case. Finally, we found, looking for other stuff, that in PDRs, for instance, this paper from David Tessier on the Horsehead Nebula, that this ratio is actually high. Not as high as this one, but it's roughly 20. So we wonder, okay, what will happen if we play with our chemical models and add some strong UV field? And this is what we made. This was increasing the UV factor by a factor of the UV field, and the ratio goes in the right direction. Okay, so you have less C4H, you have more C2H, and finally you have this ratio goes up. So this seems to point toward some sort of photochemistry. Okay, more lines. Ammonia. We had one line of ammonia from Hi-Fi. We took what we knew for when it is in principle formed, scaled that radius, and we got this very high abundance of ammonia. It is true that we didn't take into account the infrared pumping, so it might be lower, maybe one order of magnitude lower, but still plenty of ammonia in this guy. We had 2 lines of water. We suppose that this the location of water will be in the innermost layer of the 4 we had. Actually, if we add more layers, the fit won't be as good as the one we have here. And we observe a high also abundance of water. This is comparable with you have in all rich stars. We know carbon-rich AGVs have water due to probably the penetration of UV photons due to the clumpiness of the envelope, but they are not as high as this one. And finally, SIN. It has been introduced already by Thaisa the other day. We observe SIN, we have 2 lines and 1 tentative, well, and the rest we fit the no detections as well. We could estimate the extent of this species as it comes from the photodissociation of SIS, and it's roughly the same photodissociation radius as SIO, proved by Masalchi for certain objects, which is one or object falls within this category, and this is the abundance we have. As Thaisa said, there are very few objects detected in SIN. I thought there were 4. I think she said there was another 1, so maybe there are 5. IS 16 for sure, everything is there. Right? Eta Carina, we observe while studying SIA-bearing, silicon-bearing species. WQL, we got detected first by Elvira and then by Thaisa, and in this guy, FGL 2343. Interestingly enough, those are 2 yellow hypergiants, those are 2 red hypergiants, which are meant to be rich in nitrogen, and none of them presents SIN, so it's not related with carbon-rich chemistry. Okay, so it's induced by photochemistry. Okay, so I haven't seen the signs, maybe I'm running too fast, but well, just in case, I would prefer to be on the safe side. But results. We have a high luminosity, so a massive star, okay, presenting carbon-rich chemistry, probably as I mentioned, because the hot bottle burning has stopped at some moment. Presenting very intense HCN 120, despite we have maps, NOEMA maps of this line here, we have also different transition observed. We were not able to fit that out. We have to remove from the fitting. Don't know what's going on with this line here. We have this high ratio, probably related with photochemistry, very high abundance of ammonia. This has been related with swept up material, not sure because we don't have maps. Water is also has a really high abundance. As I mentioned, it can be also related to photochemistry, and SIN, once more, photochemistry. Well, probably we have a binary here, as it happens to in WRQL, and a point to think about is why, if all objects presenting these large abundances of C2H is due to some sort of binarity. Maybe not, because we don't know, we don't have C4H, we have to get for C4H and then compare and see what. So my bet here for this guy is we are dealing with a very warm massive star with no hot bottom burning and a hot component. And the future will be to try to prove this with high angular resolution of SIN in this guy, because we don't understand the thing, and see if the emission of these 2 species, C2H, C4H is decoupled and are from different regions, and so. And then prove and take play with the chemical models and to try to characterize the binary if there is any. And the next step will be to do the very same stuff we've done with IC1041, which is another HVC star, for which we have the very same set of data I just presented. Haven't started with that, but we have this data. And add more objects. There are more HVC objects we haven't observed, even in CO, but we have to try. And that's it. Thank you very much for your attention.
Thank you.
Guillermo, have you looked at the oxygen isotopic ratios and tried to see how these compare with, for example, the diagram that Javier showed the first day?
Yeah.
In case maybe an interrupted evolution can also partially explain.
We haven't detected the oxygen 18, 17 in this object. We've only checked the sulfur ratios, and we have also carbon ratios, but they are not really clear constraint. Because, so in general, it's like 50 for carbon, but with some of the species give very low. C3N, for instance, is like 7, but we are not sure on the determination of the abundances. So, but for oxygen, we don't have that. It's something to look for, sure.
Yeah, that's right. You expect it to be low.
Yeah.
But what about what is your feeling about the interrupted evolution because of a component below event or something?
I actually focus on in these processes by Amanda of the hot water burning stopping. I mean, it's something that makes sense to happen. Maybe we haven't seen any of these guys, but actually, these objects were proposed to be massive stars in the 80s, something. So, but nobody cared about that. So, but yeah, we have to check everything.
Thank you, Guillermo. I was one of those people. It wasn't in the 80s. It was the early 90s. Yes, I am so old. Comment and question, which is yes, we carried out a survey for the Zuckerman and Dyke objects. I was been Zuckerman's student. Jerry Forbay and I went to the 30-meter and observed, I don't know, dozens of these candidates and detected a lot of them. To my surprise, they were not bright IRES sources. We detected all of them, almost in CO. And we got galactic kinematic distances, which are very unreliable, but should seem to show that it was, generally speaking, a population of luminous carbon stars, which we said, aha, massive.
Yeah.
Is there another explanation possible, which is that we're seeing these stars right at the time when they're having a thermal pulse? And would that help you at all with the weird abundances you're seeing?
Maybe it's something I will have to check, but I have to also look for those sources to see what I can get.
There's such a long history. We don't even have time to talk about with this carbon star mass business. When I started looking at it, everyone said, "Oh, carbon stars low mass, less than 1.5 solar masses." And then someone said, "Oh no, high mass." And then the theorist said, "No, low mass." And so now it's 1.5 to 4.5, right? It's like this compromise, which seems to hold up. So, but if you're catching these things in the midst of a thermal pulse, maybe that's a way to get some fraction of them way up in the house.
Yeah, will be the case. Yes, but it's something to track in some way, right? Yeah. Thank you.
Yes, sir. Question: what is the isotopic signature of the H2O that you detected?
I think it was 3, a standard one. 3.
H1O16.
Sorry?
H1 and O16.
Yeah, it's
no other isotopes.
No isotopes. Yeah, it was with
T2O.
It was with Hi-Fi. We only selected these two lines, so what we have.
For CNH molecules also said you all normal isotopes of carbon and hydrogen.
For the rest of the lines of those with robust the abundance determinations, we have like 55. It's 13 carbon 13 versus carbon 12 versus carbon 13. It's around that. 50 something.
Did you study also the optical?
Sorry?
Can you see this object in the optical?
At 3, I think, no, I work always in millimeters, but I think the first image I took it from the, or I don't know if it's infrared or optical. I think it's infrared as well. But I don't know if you see that on the optical. I haven't checked.
Well, it's got a guide distance.
Well, huh?
It's got a guide distance.
Yeah, but I just so yeah, it is kind of robust now.
Lighthouse speaker again. Next up, we have Elvire Debet. Talking about dense, dusty, and asymmetric mass flows from extreme red supergiant.
Okay. This is for sure a massive storm. So I'll be talking about a particular red supergiant. And well, I hope I try to convince you why it's pretty cool to look at. So first up, the red supergiants, we're definitely away from the HB, right? We're up at initial masses of a good bit above where most people here probably feel comfortable. So we're up at 8 to 30 solar masses about initially. Cool stars, very luminous, of course. It says 10 to the 5, but let's say a few 10 to the 4 to a few 10 to the 5. But what I'm studying them for is their mass loss. So there's still plenty of questions about how they lose mass. So there are pulsations, there is a lot of dust, whether those drive it, not sure. There are magnetic fields, there's plenty of large scale convection on the surface, and we don't really know what the balance is there. However, I will not be focusing on the launching mechanism. The other main question is how much mass these actually lose. Across the entire class of red supergiants, there's multiple orders of magnitude variation. And you, broadly speaking, get two classes there, two subclasses, one with low mass loss rates. Think about Betelgeuse or Antares. They typically have active chromospheres, and you end up at about mass loss rates of 10 to the minus 6. And then you have the more extreme ones that appear as OHIR stars with mass loss rates upwards of 10 to the minus 5. And the poster child there would be VY Canis majoris, which I will bring up later, but that's not quite my pet object for this talk. But so, just like for the AGB stars, we're of course interested in how the mass loss will actually affect the evolution of the star itself, as long as it's still a star. And there's indications that we need better prescriptions for the mass loss in the red supergiant stage, because the envelope stripping will actually affect whether this star is going to finally go supernova from the red supergiant stage or whether it's going to evolve further. And then thinking about the red supernova, the red supergiants going supernova, there's also an effect on the supernovae themselves. Again, how much of the envelope is actually being stripped. So what are the properties of the shock propagation through the material, and then lately, well, or it's been established in the supernova community that they need very dense circumstellar matter ejected quite shortly before the supernova. And there's been some recent very strong indications for very strongly asymmetric red supergiant circumstellar material. So, VY Canis majoris looks like a mess. It has a lot of clumps and dust and gas. Guillermo found some high velocity outflows that basically plow their way through the regular mass loss. We see all kinds of shocks when the material or when the gas runs into some of these massive dust clumps. This causes shock chemistry, of course, that we can trace. So there's plenty going on there. But VY Canis majoris is only one. So just like we have to do for the AGB stars, we want to expand our sample a bit. Statistics are against us. There aren't quite as many red supergiants. But I started focusing on one of those, NML-SIG. So it's also a very infrared bright source. So just to set the scene here, On the left here, you this image, you see a mid-infrared image where there's kind of two lobes of emission that were interpreted as dust that is being heated mostly by the OB cluster that lies off to the mostly to the west. And the authors of this paper suggested that NML-SIG has a very small outflow, that everything is basically being obliterated by the cluster. Not true, which actually they should have already known from looking at the OH maser maps. But anyways, so there's in the OH, they found signatures of multiple components, some kind of old spherical component, and then potentially a young, maybe bipolar outflow with a northwest southeast orientation and potentially some velocity gradient there. So interesting enough source to follow up. We did that first with single dish because that's the cheaper version of observing your objects. And we saw all kinds of structures in the spectral line profiles. So this is all molecular lines, right? Across, what did we have? 15 molecular species in our paper, and then in the same paper, I don't remember how many molecules they had, but we did this independently from each other and basically found the same thing. So we need some kind of underlying spherical mass loss and then some quite directed outflows. Well, that's what you can go and infer from the single dish. So then you follow up. And then you get something that you don't understand. So what are we looking at? So this is NOEMA data at 230 gigahertz. So we were going after the CO 2 to 1 to go and see how big this envelope actually is. But I'll first look or go through the continuum here with you. So what do we see? This little star icon shows the position of the star. And then you have these two insanely large dust clumps. What we get from this is that we have about 2 × 10⁻³ solar masses of dust, which is very warm. And this actually would potentially match very well the requirements set by the supernova people on some of the not the remnants, but the shock propagation that they see. So, well, there you go. We have to check how this would actually work out, but we're happy about this. And this is actually, well, the resemblance to VYCMA was a bit uncanny when we saw this first. So I don't know if you remember from my first flipping through the images of VYCMA. It also has several dust clumps that are offset from the star. There's some dust around the star as well, but then there's all kinds of clumps around. And I don't think that these are necessarily like that these are the clumps as they will be when we look at them with high angular resolution, right? This is probably going to fall apart into a bloody mess. So, so we have a lot of dust. It's pretty warm, but because we have the molecular information, so spectrally resolved molecular information, we can also get some feeling for the location of these dust clumps, so that we have to follow up in a bit more detail. But we think that this first clump, this A clump, sits a bit in front of the plane of the sky, B clump towards the back. But there is also some kind of connecting bridge or whatever you want to call it between the two. So we have to figure out what the morphology is there, and hopefully the molecular emission will help us with that. The match with the mid-infrared data can be made if you actually move their assumed stellar position, the peak of their mid-infrared emission, to the peak of our continuum component. And so I believe that they were actually not looking at the star, but at the hot dust. So that's an important thing when we try to match up the morphologies. And so we got some extra ALMA data in a completely different project where we squeezed it in still in the last minute, and we got some confirmation of our positions and of the clumps. So we'll squeeze out whatever we can for the dust properties. So I said that we were actually looking for the mass loss, like on a large scale. So how much, I mean, not only what we trace in the dust, but so the main goal was there to look at the CO. That's what you see here. These are some channel maps. This is the systemic velocity. So we see an extent of this the CO, circumstellar envelope, out to about 20,000 AU, say. But there is clearly asymmetry with a larger extension to the southwest and a shorter extension to the northwest. So it does somehow indicate that there's probably something with the SIGOV2 cluster impinging on the envelope from that side. But I think if I show you these maps, you don't really stumble across how big it is, right? I think you're all trained to see all kinds of substructure here. So we have all kinds of blobs and arcs and shells. This is a blob that I wanted to, this pointer doesn't hold for very long. So there is a very clear blob here, right? So to the southwest, which we'll see later will nicely line up perpendicular to the other preferred orientation in the system. So that's a blob, and then we have all these arcs and shells. And these arcs and shells I'm going to try to convince you of now. So this is a PV cut through the cubes. Also here I have 12 CO in the color map, 13 CO as the white contour, just to show that the 12 CO and 13 CO do trace roughly the same stuff, which is good. And then SO2 is just an example here of one of the many molecular lines that we have, and which has its own complexity. But the cut is made along this, well, or that blue line there in the bottom shows the cut that we chose after careful consideration. So that goes through the stellar position and that blob to the southwest. And what we see here, and I don't know if you are all as keen on seeing this as I am, but what I think we see, so maybe I can flip back and forth so you get a feeling for it. But what I think we are seeing is actually multiple expanding shells. So these dashed lines basically just show the signature of a spherically symmetric shell expanding at a given velocity, given radius. And importantly, what I see here is that I get a velocity gradient over time. So you see that the shells closer to the star are more extended along our velocity axis, right? So we're seeing that this material is accelerating over time. There's no obvious way of doing this unless, I guess, your stellar parameters are changing, which, I mean, this is over 2,500 years. We don't have information on those timescales. But then another interesting thing is that, sure, along this cut, I get these shells with this size and velocity. If I take the cut at different angles, the velocities that I recover are the same, but not the sizes. So we're not looking at something spherical, we're actually looking at something that is probably elliptical. And elliptical with an elongation perpendicular to this cut. So this is again this preferred orientation that they also saw in the masers. So my suggestion, and that I made in the paper, is that there's probably a binary system in there that we have no other trace of yet. So that would still need to be confirmed in different ways. So in summary, we have an extremely large circumstellar envelope, high mass loss rate, 10 to the minus 5 background, and then enhanced mass loss up to 10 to the minus 3 over several decades to a few hundred years. Plus then these shell modulations that we don't know if it's the star actually changing its mass loss or some companion shaping the mass loss. That we don't know. Then we have this very warm, large mass of dust. How often does this happen? Now we trace the clumps very close to the star. Maybe there are some further out that we're not seeing. And for those of you who are into supernova remnants, maybe this might actually be the early phase of what later could become the green monster. So let's see what comes out of whatever modeling we undertake there. And then I just want to still give a shout out to Mark's poster again. This is also supposedly a red supergiant, but it's a bit more messy than mine. So thank you.
So do we have any?
Why, these are very interesting results. Why did you not fit a spiral instead of like concentric arcs or shells? A spiral would give you the binary period.
Because a spiral doesn't really match what I see in the PV diagram either. So I mean, it's
But a spiral or some 3D spiral rotated at a certain degree.
yeah, it's so the PV diagram is not really clean enough, I feel, to do that. And then I feel there's a risk of going a bit too quick, too far in drawing conclusions on the binary there. But something we can maybe try.
Could it be that you have you tried to watch the proper motion on the star? Could it be that what you are watching is a bow shot and it's moving in this direction away from the cluster?
No, the proper motion is such that there is a bow shock, which actually hasn't been published yet, but there is a bow shock to the southwest, roughly. So this is not, and that's like way outside. So some completely different scale.
How many of these things are there, you think? This messy, massive-ish star with enough structure, probably down the line, you can actually start understanding.
I don't know. The statistics aren't very good on these. There aren't very many. So we have I don't know. A handful. Yeah.
I was just going to ask, for the outermost shell that you identified in that plot, it was kind of more visible in your initial image on one side than the other.
Yes, it is.
We
We don't see for that largest shell, we don't see it at all on the other side.
Yeah.
Yeah.
I was just going to ask, do you think that's another sign of asymmetry along another axis, or is that just sensitivity of CO in that region?
No, I think there's actually just something going on that scale that is different on that side of the system.
Like a spiral.
No, I don't think that would match that, but sure, if you want to.
It's just because the symmetry axis didn't match the original one that you showed from the northwest to the southeast. Do you see what I mean?
No.
So when you drew the PV diagram,
Yes.
maybe I'm misinterpreting it.
Yeah.
But
I'm doing that along the southwest northeast cut. So
it does-
perpendicular to.
so it does match the.
So I get the smallest radii along this cut.
Yeah.
And the longest radii along that cut. So that's why I think that it's potentially a binary on an orbit along an orbital plane northeast, southwest, yeah.
Okay, good.
Okay, let's thank our speaker again. And next up, we have Alec Tsukai, talking about investigating PN using central stars, extinction and binary.
Yeah, bye. Great, thank you.
Hi everyone, I'm Alec. I'm a student of Albert's at the University of Manchester, and I'd like to thank the organisers for giving birth to this wonderful conference. I'm having a really lovely time, and I think some really exciting science is happening. I'm going to be talking about some work that I've been doing that has recently been accepted for publication in Minerans, and you can find the paper on the QR code. Mostly looking at extinctions towards planetary nebulae, and I'm going to be using a Bell 20, which is this spherical PN there. To kind of exemplify some of the problems that we've been having. So the reason that we care about this is because we really want good extinctions in order to be able to properly characterize RPN. If you've got the wrong extinction, you get the wrong luminosity. And if you get the wrong luminosity, you've got a whole host of other problems. You don't really have a constraint on your evolutionary history, your chemical enrichment, so on and so forth. We're also interested to see if we can unpick the interstellar versus the circumnebular extinction. Because circumnebular extinction has recently been suggested as an explanation for the high-end luminosity cutoff in the planetary nebular luminosity function. So a quick briefer on extinction for anyone that's not particularly familiar. Extinction obviously has a wavelength dependence, it has a reddening effect, and it's normally characterized by a number of different dust extinction laws. We adopt Fitzpatrick 1999. And one of the results of this work is that we find that actually the choice of extinction law has a really big effect on some of the results that you get through extinction, especially if you're looking at Barnard-Declermont derived extinctions. So that's something to be cautious of. In this work, we simply adopt the RV of 3.1, which is the galactic standard. And we have a couple of, oh, that's really pixelated. We characterize it in a couple of different ways. We use C beta, which is the logarithmic extinction at H beta, which is commonly used in the PN community. We also use EB minus V, which is your color excess. So your extinction at Johnson B minus extinction at Johnson V. And that's more commonly used by extinction people. A Bell 20. There are a number of different ways of determining extinctions. And I'm not going to go through them in detail, but essentially there's a really wide range in the literature determinations, and this is a problem. And so we want to resolve this. And so what we've been doing is we've been looking at the central stars. So central stars are obviously very hot, and this means that in the optical, they have really consistent photometry over different, the shape of the spectrum is quite consistent over a wide range of temperatures. So a standard shape can be assumed without introducing too much error. And so we adopt the TMAP 100 kilokelvin model. And for our sample, we find that that introduces an error of about 0.02 in EB minus V. And so if you assume that all CSPN have this intrinsic shape, then you can then look at any difference from that shape and attribute that to extinction. And so that gives you a measure of your extinction values. So this is our procedure for a given planetary nebula. So we get a CSPN identification from either Gonzalo and Santa Maria, or from Chorney and Walton, or some of them are our own. And there are problems with that, as Quentin touched on earlier. But what we then do is we generate a SED using PySet. And PySet is a code that was developed by my co-supervisor, Ian McDonald. And it uses a stellar identifier in a given catalog, and then searches for it in a bunch of other catalogs that you tell it to search for. And it collates an SED from the broadband stellar photometry in those different catalogs. As I say, we use the TMAP 100 kilokelvin model to fit these stars. And we look for the extinction. So we fit the model to the SED, both through a couple of methods. So Nelda-Mead optimization, and MCMC, which gives us a handle on our uncertainties. And this gives us an extinction result. So I'm going to show some examples of these fits. My images have unfortunately not gone properly, so they're quite pixelated. I do apologize for that, but hopefully you should still be able to see. So this is a Bell 20, and this is a really well-fit nebula. So we're able to get a pretty good constraint on our extinction here. And we get a C beta result of 0.11 plus minus 0.02 or so. And this is a relatively low extinction nebula, and the photometry is all very consistent there. So that's great. Up in this top corner here, we've got another pretty well fit nebula. This is a higher extinction result, however. and you do see the 2175 angstrom bond, which we're able to well reproduce, and that implies that our V value is successfully assumed. You know, the 3.1 is good. You can see here, it exemplifies the photometry pretty well. So the SkyMapper data, which is the cyan circles, that's more scattered than a lot of the other photometry. And you see some of the problems that we have with IR photometry. So we don't fit IR, we only fit data points up to 10,000 angstroms. And that's because, so the VHS data points there are very well reproduced by the model. However, 2MASS, which has a relatively wide aperture, is not well reproduced, and that's because often the IR photometry picks up some of the nebular emission. This plot, on the other hand, is a purely fit nebula, and some of the nebulae that we look at, the photometry is just not fittable. This might be a really interesting SED to some people in the room, I don't know. But we're not able to get an extinction result out of this. And so we need to have a quality of fit metric to be able to discard the ones where we're not getting good extinction fits. So the method is pretty accurate. In the best cases, you get down to 0.02 in E-beam SV. It's homogeneous. You can apply the same method to a large amount of different nebulae. It's specific to the nebula, it's distance independent, and it's relatively broad. You can do it from a lot of different sources. It uses a wide wavelength range, and it can go beyond dust maps. So we've applied the method to a sample of extended nebulae, and we chose that sample for a couple of reasons. The first is because we wanted to avoid nebular contamination of the SED. So it in general works better for lower surface brightness nebulae because the photometry is better quality. And we also wanted to choose hot CSPN. So these are larger objects which are more evolved and therefore have hotter central stars. So the assumption of 100 kilokelvin for the central star is more valid. So we've taken the complete sample of extended objects, which there are 262 true PN in hash which fulfill that criteria. Of those, we're able to identify a CSPN for 255. But relating to the problem that Quentin discussed earlier, we find that a lot of those CSPN identifications are at least a little spurious. And so we've got 162, which we're actually fully confident in, plus 7, where we find that the SED looks composite, and I'll return to that later. Of that 162, we're able to get good fits for 130, and we define good fits as being SEDs with more than 5 data points and with a naive reduced chi-squared smaller than 5. And so when I say naive reduced chi-squared, that's when you assume a error on the photometry of 5%. And we do some bootstrapping to get a more accurate chi-squared as well, but that's our quality of fit metric. And so compared to some of the existing extinction determinations, you can see some of them are really bad. So this is the extinctions you get if you take the ESO Strasbourg H alpha tau H beta line ratios. And I mean, some of them give you negative extinctions of more than 1, which is completely ridiculous. And so, I mean, this is just to show a really bad example. And then some of the literature extinctions we do find are pretty good. So David Frew's compilation that he made for the calibration of the 2016 surface brightness distance relation, that actually comes out very, very well. I do have some problems with that data source in that it's not particularly well documented, so it's hard to tell where the data is coming from that. And so it's hard to reproduce for new nebulae, but it is pretty reliable. I think we're probably more precise, but it is a good data source. We also find that dust maps tend to be pretty good for these nebulae, and Condon and Kaplan's 1997 radio extinctions are also pretty good. They're for quiet objects. There are also some other results that we've managed to do to generate from our SEDs. So first of those is the luminosities. So Pi said if we've got a temperature for the source, we're able to calculate a luminosity for the object. and then we plotted them against Marcelo's cooling tracks, and they agreed pretty well. We don't love the literature temperatures in a lot of cases. Yeah, but so we compared using the luminosities. We then evaluated some of the binary candidates, post RGB candidates, which have been identified by David Jones within the sample. And we don't really love any of them as post RGB candidates. So Abel 46 has quite a wide range of temperature determinations, but the highest and probably most robust temperature determination of 83 kilokelvin places it just below the post AGB cooling tracks. HATR4, we just find that it lies on the post AGB cooling track, so there's no real need for post RGB evolution for that source. Harvey 13, which is the kind of the most major outlier there. We find that its post RGB candidacy really comes from a single temperature determination of Napovotsky 1999. And I've been discussing this with Semi. And so this temperature determination has the kind of the same problems that he was discussing in his talk yesterday. And we think that it could quite likely be a lot higher. So we don't really find any need for post RGB evolution in our sample. Just through visual inspection, we were able to identify some of the sources in our sample as being binaries. And we do a multi-component fit to these. So we fit the UV photometry using the central star, and then we subtract that from the rest of the SED and fit the remaining photometry using PySeb's ordinary fitting functions. And that gives us a luminosity of the CSPN, a luminosity of the main sequence star, and a temperature of the main sequence star. I'm claiming that there are 4 new binaries identified here. I received an email on Monday telling me that 2 of them embarrassingly had come up in the list before. So it's actually 2. But I think we are able to kind of add to the strength of the candidacy of the other 2 as well. And we've performed a binary analysis on our sample on the basis that it should have a different set of biases to conventional samples which are analyzed for binarity. And we find it in the complete sample. We have 23% of our sources being binaries. But we also note that, so if you're looking specifically at objects which are outside of the galactic plane, David Jones's catalog has 22 such objects, 16 of which are in the north, so north of the galactic plane, which is probably more than you'd statistically expect. We add 1 to that. And so we speculate that there could be some bias in our binary detection based on greater surveying in the north. But we find that there are 36% of a binary fraction of 36% north of the galactic plane, which is then approaching the main sequence binary fractions, which were calculated by Offner et al. In 2022. So that kind of region in the graph is what's relevant there. We find that extinction, for most of our sample, the extinction is dominated by interstellar, but we find 1 source that is a major exception to that. And we do some very crude analysis on that, where if we take the difference between the 2 sources and then assume that that is circumnebular, and then extrapolate it to the size of the smallest galactic PN, you get a C beta of 1, which is double what's required to explain the PNLF cutoff. And we speculate that if it is circumnebular, then we need extinction morphology in order to be able to explain what's going on here. And I will just leave my conclusions on the screen because I'm out of time.
It's a very good talk. I was wondering when you talked about how you had a few where the SED made it visually obvious that you had a binary and then you fit the extinction. For SEDs that are less obvious there's a binary, would your codes be able to kind of tease that out, or you think?
So those 7 sources, they were selected by hand. So I've kind of gone through and looked at the ones where you've got obvious UV emission, even though the optical photometry looks like a star. The ones where maybe it's less clear cut, we're not going to fit a good extinction to them. And I guess the hope is then that our quality of fit criteria would then lift them out of the sample. But I reckon there probably are some really interesting objects amongst the set that we've delineated. It's just we can't fit extinctions to them.
I suppose, put another way, would failing to fit extinctions to them kind of indicate maybe to look a little deeper and see if there's a binary? Would be a better way to put my question. Or is there too many ways it could fail for that to be?
Yes, but yes. So both are true. So probably yes, we could probably do more work on that set of discarded objects. But there are some cases where the photometry is just bad, and that's the reason for a poor fit, as opposed to binarity. Yeah.
David in the back.
Thanks. Yeah, really great talk. And just to build on that, I think that something you have to bear in mind for most of the population of binaries that we found, at least the post-common envelope ones, the companions are very late type. So it shouldn't have that dramatic of an impact on the extinction that you're measuring. The ones that will have a standout, which I think most of the ones that you will find there are probably things with early type companions, where they will be much wider binaries, which is a really interesting thing too. But if you go back to the plot you showed of the 3 different objects with the different qualities of fits, right at the beginning, sorry.
Yeah.
Like the last one, the bad one, you could potentially explain some of that not just by bad photometry, but if it's a very compact binary with a very strong irradiation effect, you can get a very big scatter in the catalog photometry. So those would be really interesting systems to look and see if, I mean, the points that really look crappy there are from Pan-STARRS. So it might be interesting to see if in Pan-STARRS there is because I guess that's combined from all of the images in Pan-STARRS, right?
Yeah, it will be
the magnitudes. So whether there is significant variation between different epochs in Pan-STARRS, so that you might be able to fish out additional binary candidates just by looking for scatter in those.
Yeah, thank you. Thanks for your talk. I have a question with the temperature. Is that an input or is it an output?
For at which point?
The temperature, because it's correlated to the extinction. So if you have a hot star, you need to extinct more to fit the photometry.
So for our generic stars, the temperature is an input. So we assume 100 kilokelvin, and we assume that has no massive effect within the UV and optical. We find that gives an error of about 0.02 in EBV.
Only.
That's, yeah, compared to the 60.
You just fix the slope, not the.
Yeah, it's just the slope that you fit.
Yeah, but the hotter star has a higher slope, no?
Yes, but the difference is, yeah, the difference is most.
So the slope is so sensitive. Yeah. So you're just looking at the optical. I mean, by the time you look at the UV, that's also the optical one share of road.
So sorry, this isn't very clear, but this line here is the daylight spar UV. And so even, I mean, there is a noticeable difference at 30K when you normalize them relative to one another. But once you're above 60, which is kind of the minimum that we assume, and is roughly consistent with. Yes. Yeah. Okay.
Okay, let's thank our speaker again. Martin has an announcement.
Yeah, okay, so there is a piece of information I'd like to share with you. So in case your flight departs from Madrid Barajas, there is a strike on the security control. It takes much longer to go through security. So in case your flight departs from Madrid, so it doesn't you don't need to care if you have a connection flight there, departing from Granada, but if your flight departs from Madrid, try to be at the airport well in advance.
For how many days?
It's been a long period now, so we should expect in the next day that they still are on the strike.
Okay, now we have the discussion session, and to start us off, Noam has some slides to show us.
Yes, so I pose a question on Slack. Say we have discussing a planetary nebula, which is a legitimate object for our meeting. And by 8 p.m. 10, the central star explodes as a type 1a supernova. Does this object belong to our community? And only 18 people answer, and the answer is yes, but it's not trivial. Imagine people who study star formation. Of course, at one point, the star would form on 5 solar mass will be a planetary nebula, but we don't see here people studying star formation. Yes, it will become. So it's not trivial. But I'll tell you why I think it's, yes, it belongs to our. So I call them SNPs. What is SNP? SNP is supernova 1818 inside a planetary nebula. Here we have 3 planetary nebulae. Here we have 3 supernova remnants, type 1a. What type 1a is an exploding white dwarf. There are different scenarios for that type 1a. The advantage of each one of them that it has problems. So we have lots of to do there in the community. So there is no agreement what actually brings the white dwarf to explode. So what you see here, I showed you 3 type 1a is what we call ears on 2 sides, opposite sides. They are not so nice as in planetary nebulae, but it is expected because usually they are larger, they after explosion, and also they interact with a larger medium. So my suggestion for this is actually that all of them, because the expectation is the white dwarf explosion will not have this structure, is that they exploded into an old, very old planetary nebula, 500,000 years old, or so, or 50,000, but maybe the planetary nebula was there before the explosion, maybe already was completely neutral. Okay, look at this one. This is a paper from last year. The title is A Supernova That Destroyed Its Planetary Nebula Progenitor. Here we have 2 ears, one here, one on the other side. So I draw these lines that you can see here. Okay, on the lower right, what you see is that what I took it from the upper part and rotated by 180 degrees, so then moved it, but a little bit more, you know, we have bent asymmetry, and you see quite nicely fit. So again, for this one, I suggested that paper that this was a supernova 1a exploding inside the planetary nebula. Here I have a list of some, I will not go through it, this is paper from 10 years ago, but 3 years ago I updated it and claimed that more supernovae exploded. And this is a Parker Thank You supernova remnant, but it's Quentin put it not in the direction, so I rotated it here. And what I would like to point out that when a white dwarf explodes, it doesn't have hydrogen. This is the definition of type 1a, no hydrogen, but some other elements, like, you know, lots of iron, half a solar mass or more of iron is formed. And here in this planetary nebula, it is elliptical with some structure inside, but the point is that there's lots of hydrogen around it, so it is interacting with an hydrogen. And for other arguments and so on, some people claim explosion was shaped by a binary white dwarf interaction, but I don't think so. So what is a fraction of SNP among all type 1a? I claim more than 50%. I think this is my own view. It's strongly supported by my wife and kids. is that most type 1a explode inside planetary nebulae. I need to convince that community, but remember, in that community, there are five different scenarios of type 1a, and each one is attached personally to the scenario he loves, so it's very complicated. Now, let me go back to what I showed in the first day. We have also core collapse supernova. These are massive stars, and also some people mentioned here. So I don't want you to confuse. They have different structure, highly departure, you see in 87A. But one example I showed, battery is going down. This is highly deformed, look like really deformed planetary nebulae, because I think the explosions are by jets, so they are much more deformed than the type 1a. The type 1a are more, let's put this, are more spherical explosion into a planetary nebula. This is what I had to say. Yes. If there are comments, I will be happy. I think it's very relevant, and I will be happy in future APN meeting will have some people who study supernova remnants. But we might have a fierce discussion. But yes, because I'm not used to some of the terms that we have. No, that's
I like this scenario, but how can you explode a white dwarf inside a planetary nebula? Does it have to be white dwarf merger, double degenerate, or accreting from a companion? Because accretion now, as I show, is less efficient now with the geometric correction factor.
Yeah. Well, if we get to the explosion, this deserves a talk by itself. There are 5 different scenarios. A regular star called single degenerate can be giant domain sequence, but not degenerate, transfer mass to a white dwarf, and then the white dwarf explodes. It was popular 30 years ago, and from my point of view, it explained not even one observation, okay? It's a fact, but people like to quote it, because I don't know what. Second one, you have 2 white dwarfs merging and violently explode. The third one is that you have one white dwarf transfer helium to the other one, and the other one explode. And then there are the fourth scenario, collision of 2 white dwarfs that are not bound to each other, come and collide. This can explain at most 1 in 10,000, so it doesn't work. But the people who suggested it love it. Okay, and the fifth one is my idea that I put 15 years ago. It's called the core degenerate. You have common envelope, and the white dwarf merges with the core of the AGB star, and it gives you actually the second mass white dwarf rapidly rotating. Eventually, it explodes after it loses angular momentum. 2 years, in one case, suggests 2 years in a paper from this year, can be 10,000 years, can be 500,000 years. So this is why I think the core degenerate, the only one can explain all this. But I mean, there are 5 scenarios. Everybody loved with his own scenario. So to be fair, this is my scenario, but I cannot tell you that this is accepted by.
That's an interesting scenario, but does the timing work? That you have to expel the planetary nebula, and then that should happen no more than 10,000 years later, 20,000 years later.
Why could it be 500,000 years?
Well, but then you don't have the planetary nebula there anymore.
Why not?
It's too diluted.
You still have it. It's not ionized anymore, but you have the material around the cloud distance, several parts.
So then you can study that in the remnant, much further away.
Yes, you interact with it's an old, remnant of a planetary nebula. It's already neutral, but so an old planetary.
In that case, that would be quite difficult to study. So.
You have now the interaction, so studying the shaping and mass and so on.
Do you know there's a paper, I think by Jura, I think it's 2001, in which he compares the structure around the yellow hypergiant FAGL 2343 with the Kepler nebula and finds that they really look the same. So he proposed, in fact, Kepler nebula is it comes from the core collapse of a yellow hypergiant, a pretty massive star. So have you checked this objects as well? I mean, how they emit the jet material in these massive late phases, and how will create these type of bubbles?
Well, you asked for your pointed paper.
I bought this paper and I wonder if you check this could fit for
I
massive stars.
don't remember seeing it. Can you put it on Slack or send me an
Yeah,
email?
I will put it on Slack, yeah.
Or send me an email or put on Slack.
I want to make 2 points. One, I discussed with you at coffee, but for the general audience. So one should explore the modular SNPs, one should explore the kinematics of the expanding planetary nebula shell based on how much momentum is being injected by the supernova explosion into this shell. Does the velocity of the shell and the momentum of the shell make sense? And the second point is this very long time scale that you're quoting. I think this is virtually impossible because by the time the PN shell is so tenuous, it has merged with the interstellar medium around it. So I don't think the PN shell will be even maintained for that long. We don't see such long, large, or old PN shells in regular planetary nebulae, right? Which we know they're what 1,000, 2,000, 3,000 years, but we're not seeing 100,000-year-old PN shells amongst the regular sample PN that we have. So I think there's some difficulties with what you propose.
The one I showed in the next slide, wherever it is, there is also in Kepler. Let's say there is agreement that there is a hydrogen here. Okay, so the question, what is this hydrogen? Okay, so those who support the single degenerate say you had a giant that lost the mass, but it doesn't work here because cannot lose. Not in none of this supernova remnant you see any companion that left, so it doesn't work. So this hydrogen comes from somewhere. So you can claim the interstellar medium, but there was a white dwarf here explain material. So I don't claim that the mass here is only the planetary nebula. It was a planetary nebula that swept some interstellar medium and we interact much later. Something will happen with the planetary nebulae we study. Eventually they will disperse completely. But before they disperse completely, they have some influence on the interstellar medium. They can sweep 5 times their mass before they completely lose their shape. So maybe we had one solar mass of, usually in my scenario, the common envelope is the 2-3 solar mass envelope. So you expel 2 solar mass envelope, interact with another 6. Maybe you have 8 solar mass here. I don't know. I need to work the numbers, but I don't have enough observation. We need more observation. We don't need more theories. We need to kill some other theories. So we need to kill theories, then have the correct observation.
Well, mine is kind of a naive question. If we assume that this happens during a common envelope event, and you require that there is still a leftover planetary nebula material, that will mean that both stars have to be kind of the same mass in order to not waste so much time for the explosion and the explosion interacting with the remaining planetary nebula material. But how likely will that be? How probable will be that both stars have like kind of the same mass or same age?
One star is 3 solar mass, the other one is 2 solar mass. The 3 solar mass evolve first, transfer 2 solar mass, say, just an example, to the other one, 4 solar mass, form a white dwarf. Now the white dwarf spirals inside the envelope, merge with the core, and eject the planetary nebula. Just an example. So eventually you're left with one massive white dwarf around the Chandrasekhar mass that is a remnant of the merger of 2 white dwarfs. I don't claim this scenario is closed, maybe it cannot work, but I say that when you look at shaping and the mass, this is the best one that goes with the shapes and the interaction and the shaping of through the interaction. This is my claim.
So let's also remember that we can discuss all the talks from the afternoon
Yes.
sessions as well.
Just to comment that last year we published a paper of explosion with supernova inside planetary nebula. And 50% of the supernova remnant are consistent with explosion inside planetary nebula. And the other 50% are not, are like a normal interstellar medium.
Norm's number.
Huh?
Norm's number accepted by his family.
Anyone want to comment on anything from this afternoon?
Is someone interested in discuss something about astrochemistry or UV X-ray driven astrochemistry? Absolutely.
Okay. For answering the question that why the UAE bands of the fullerenes are all very, very broad, which is a broadening mechanism that we don't know. And it also for answering the question that what is the phase of fullerene? Is it in a gas phase or is it in a cluster, which is few fullerene attached to each other by van der Waals force, or is it a macro or nano-sized crystal? There are a very interesting experimental work done by Hungarian scientist Laszlo Nemes, 1994 has been done, and those he published some of them. The original very systematic experimental work at different temperatures, emission of the fullerene at different temperatures, and the original spectra has not been with him. Stay in United States has not been published by the people which has done that. Just a few months ago, I contacted the Laszlo, what is the situation? So we contacted the US. Are these excellent data available? Because if it is available, we can get all those data. Then we measure all the natural broadening which Laszlo has done, emission data. And then we can map it out to any of these planetary nebulas which contains the fullerene. We can get to the point that how the UAE bands of the fullerene was created, a little bit of the, even if it match, even if it doesn't match to the experiment, again, we can have a better scenario. We move forward with the US lab, and they try their best to get those spectra back. Now, all the files are available, everything is available. Unfortunately, they cannot convert the files into the spectra that we can get these excellent information. Now, we may need help. Anybody in this room wants to help to unlock this mystery, because the treasure is there. Excellent systematic experimental work, emission, gas phase. And if we get those data back, do the mathematics, just see all the FWHM, the broadenings, it is massively increased our knowledge about the photoionization, the broadening mechanism. It is so important. So I hope that my message, which is not a discussion actually, maybe some of the astronomers, young or the seniors, can help to unlock this mystery. So the data is there, the answer is there. Albert mentioned about that if the fullerenes are in a dust or it is in what?
That must be gas phase instrumentation.
We don't know. What is if we if we compare the UIE bands, basically the wavelengths with the solid phase and with the gas phase, there is spectroscopically there is not much between them.
In the solid state, they have no rotational freedom, so that there's no rotational contours in solid state.
Now we don't know whether because the interstellar is cold, that those rotational.
It's cold. It's low excitation. It's not cold.
Yeah, so that is what I say that we can have these experimental data back and we see.
Those are vibrational because you say different temperatures, but we measured it for high temperatures.
No, low temperature also available. No.
And we now have, but we have actually rotationally resolved spectroscopy personal device. Brian Changala has measured sure.
Do we have the microphone there, please?
Yeah, so we have better now. Brian Changala has measured the 8.5 micrometer rotationally resolved in the lab at low temperatures. So that allows to characterize essentially almost all the spectroscopic parameters. The emission data that Laszlo said was at mostly higher temperature. He did actually compare to the solid state measurements at 300K in terms of wavelengths. Those bands are broad, but they're broadened by a different mechanism than what we see in DC1. And there you see rotational structure in the band. So that's just not possible in solid.
Well, not just from TC1, generally the broadening mechanism can be saying by comparing those experimental data with whatever we have.
But it's not the same mechanism.
That's
There's also
what we need to see.
Yeah, but there's also experiments on photo detachment spectra of C60 minus, for instance, and those also show that depending on the incoming photon energy, it's up to 4.5 eV. Most of the photon energy goes into the electron. At higher energy, you actually leave neutrons C60 in vibrationally excited states that then cool in the way that we think we also see it in space. So those would be the experiments to compare to. Those are not rotationally resolved, but they're vibrationally resolved.
No question that we need to have all these data come, and then we get a better picture. So that's my message. So we have this treasure. We have this treasure.
Any other comments on laboratory astrophysics or observational astrophysics? Let's just say astrochemistry. Anyone? Yeah. Meantime, I think it's exciting to look for binaries through, NS, SIN, SIC. If anyone has any.
I actually don't have a question about astrochemistry. Guillermo, do you look for these HPCs? Could they be super AGB stars?
Yeah.
Because I mean, now you considered the models up to 7 solar masses, right? And then the super AGB stars are this thing that we never talk about.
Yes.
Because we don't understand them and we haven't confirmed any. So yeah. But what mass do you actually have? Because you talked about massive, but it wasn't clear to me where you really drew the line.
So with that, on the tracks. So the range would be then. Well, taking different tracks, I was just wondering around. I found that the range would be from 4.5 to 9. So
then I have a question. Because the thermal pulse models for the super AGB stars give you timescales of about a few hundred years between them. That you should be able to trace in the circumstellar envelope. So do you have any spatial information on the molecular envelope or on the dusty envelope? Go for it.
Yeah.
Because that would be really cool.
Yeah.
Because I considered that when I was looking at the NML6 stuff, but it just doesn't work. We have to be at much higher mass, but the time scales would in principle have worked. So that would be really awesome.
be able to trace along the direction there. The Noema maps, right? The Noema maps will have, the resolution is not that high enough to know this. Even we have not resolved the whole of this T2H shell, so that is something we want to do, yes, sure.
It would also be interesting to compare with like nuclear synthesis models with Carolyn Donoghue. I off the top of my head, not sure what that shows, but.
Yeah. Just a bit unrelated comment, the abbreviation HVC is taken already. It means high velocity cloud, you're going to get a lot of confusion if you call it that like that.
Okay, so we need a better name for Guillermo's object.
Luminous carbon star. How about over luminous carbon stars?
Oh, thanks. What?
What piece?
Anyone else want to comment on it? Okay. I will tangentially be up.
Going back to the red supergiant star, if I have another question, if there's no binary, although I think it is unlikely that there's not a binary there, what will be the ejection mechanism to produce this anisotropic with the red supergiant?
A good question. I have an answer to it. So the thing is that when Jesus asked this question, I didn't give the right answer because I had considered a spiral, of course, but the problem was that I see symmetric. I mean, I see it symmetric in the PV diagram, which does not work with a spiral. Then you have to see a shift, and there is no shift. So first off, it doesn't seem like it's a spiral. Good. So that suggests that there's some kind of mechanism that makes the star lose mass or increase its mass loss over the entire surface of the star, which then made me think of thermal pulses. That's why I went looking into that, but that doesn't work for these massive stars according to the models that there are. So I don't know. Then, well, no. Next thing that I then checked was some hydro models that Camille Landry did for BYCMA, where she had a grazing main sequence companion, I think it was. And that kind of gave some
Like an
episodic, yeah, so some episodic increase in the mass loss rate. But also not satisfactory, I would say. But it's something to consider. And then the fact that you get the velocity gradient, which I then said like, well, there's potentially stellar parameters changing. I don't know, maybe if there is a binary companion, maybe the parameters of the binary system are changing, and maybe that thing is spiraling in. I don't know. But that's taking it potentially too far with the data that we have. So let's keep our eyes open and our mind as well.
What was the timescale between your shows?
It's a few hundred years, and they get, oh yeah, they also follow each other. They follow each other up faster over time, so it kind of halves the time scale to consecutive shells. So that's also something that is a bit annoying. It's not periodic. It goes faster and faster and faster. Not only in velocity, but also on time
So
scale.
the separation is decreasing in time.
Yes, in time, yes.
Okay.
I'm going faster than the material.
An eccentric binary orbit would explain that, because you do get kind of like spherical shells, more or less, when you have an eccentric orbit of kind of edge-on-ish. So I would say.
Yeah, I want to comment about that I have read some works that said that when you have a titanic encasement mass loss because of a binary, then apparently the rotation also encases on the star, and then the mass loss is now focusing on the plane, on the orbit. So maybe it could happen that.
But then that's more of a problem, because I actually see the shells more as like proper shells, and otherwise I would have to see a concentration.
But towards the plane, that's only the close binary. More distant binaries, you don't have that as much. You can have the spherical shells.
Okay.
Depending on the inclination.
Well, a good mechanism is coronal mass ejection. I mean, we have in the sun. Imagine to have a sun up to Jupiter, no? Coronal mass ejection in a supergiant could be a very good way to.
But if you look at the scales on which a coronal mass ejection happen, they don't involve the entire stellar surface, right?
Well,
So-
compared to the sun, so imagine.
Exactly, then you get these directed, so what are we talking about? Because if it's these directed enhanced outflows, then yeah, maybe that's where we have to look indeed. But if it's about these, the shells that we get, so there's a lot of things going on at the same time here. So the blobs, yes, I would think that it's probably something like that, because for the red supergiants, the scale of the convective cells is like, I mean, it's what, 30% of your surface area of the disk. That is a convective cell. I mean, they're enormous. So there's likely something there. However, then you need to sustain this over long enough time. So that might be then the next issue that we need to solve.
Actually, for BYCMA, we saw some kind of ejections, like 5 or 6 in different directions, and we claim it could be due to this kind of coronal mass ejections, and so the momentum, knowing the magnetic field we had in this object was relatively high, fits. The momentum you move in these ejections fits well with the magnetic field.
It's good that Guillermo and I are sitting next to each other. We did not detect X-rays from PYCMA. And so we put some kind of limits on this sort of global corona it might have.
You didn't look at mine.
What's that?
You didn't look at my source.
Which one? Oh,
And
and I
also-
thought we were talking about PYCMA.
But they're probably very similar, it's just that I don't have the resolution to go as deep as we can for BYCMA current. And it's in the north, so
Well,
that's.
to
where
for
it is.
H2S.
I love that.
So, nice to hear. How's the magnetic field in November?
But I don't know if we actually have a good, I mean, we're gonna try to get that from the band 3 data.
Okay.
But I don't think the data were actually good enough for that.
Well, I remember, okay.
Hey, we only have 5 minutes of discussion left, so I'll let Mary have the last word.
Yeah, Joel and I looked for magnetic activity through X-ray in the NGV star, not super giant. But one of the suggestions was to have a magnetic cycle like in the sun, but for much longer time scale. Now the magnetic field can have reconnection, but I don't know if in giants. But also if the magnetic field can act like in the sun, it forms cold spot, cool spots. And then you have enhanced dust formation. And this happens not spherically symmetric, maybe to the entire star, but most of it. So we should go back to check of magnetic, in the sun it's 11 years, nobody know how to get it. But in giant, 11 years, let's put it on, it's 100 times the rotation period of the sun. So if we have red supergiant, which was spun up by a companion, we don't have any more companion, but it has very strong convection, as you mentioned. So we might have a very strong magnetic activity. I don't know about reconnection because it's a giant, but cold spots of enhanced dust formation, this might take place.
Is the fact that we saw in BYCMA what we see, we like to see, when we publish that. We have a point in the photosphere that gets cold because of these cold spots. And as the star rotates, creates an ejection which is flat, which was something we found. We found flat ejections in different directions, what had as just like they were connected with the latitude. Okay, so you have a rotation and it will be flat in this direction, and so. And this fit the observation. We made a simple model, just having an ejection with rotation, and we were able to fit all the jets we observed. So what's in the right direction?
I think that both coronal activity and atmospheric activity is a very interesting field for the future, so we can discuss it more tomorrow. It's almost the time, so we can finish here. Thanks.
Yep, so good discussion, everyone. It is. Exciting.
Several points in this discussion, I'm seeing people sort of arguing by analogy, please do not. There's no really accepted basic shape, more analogy between say, a galactic active nucleus on one of these planetary heavy objects. And you should do the same thing in the sun. Magnetic activity in the sun is a subtle interaction between the global dipolar field anchored in the core of the sun and the turbulent convective layers out there. If you can show me that these giant stars have the same hydrodynamic configuration, you can have this kind of coronal ejections. But if you don't, you don't.
And let's wrap it up today. So don't forget to go to the Alhambra ticket office at 7:30 if you are one of the people that get to go to the Alhambra.
9:30.
9:30, sorry. 9:30.
Wow.